This is Bob Capetta from the University of Illinois at Chicago, and this lesson is Math 121 Pre-Calculus Final Exam Review Part 2, Problem 14. We have three complex numbers, 2 minus 2i, negative 2 plus 2 root 3i, and negative 5i. We want to plot them on the coordinate plane. This is the real axis, and this is the imaginary axis. So 2 minus 2i is 2 in the real axis, negative 2 in the imaginary axis. So z1, 2 minus 2i, the point will be plotted right about there. z2 is negative 2 plus 2 root 3i. Well, let's see. So negative 2 in the real direction, 2 root 3 in the imaginary direction. Let's see, root 3 is about 1.7. 1.7 times 2 is about 3.4. So we go up 3 and a little bit more to get z2. And then z3 is negative 5i, so it's nothing in the real direction, but negative 5 in the imaginary direction. So 1, 2, 3, 4, 5. z3 is about here. So we're able to graph these points, all these complex numbers, on an xy plane, on the complex plane. We can also express them in a polar form, which is going to be very similar to what we've done earlier. So I have z is 2 minus 2i, so 2 over in the real direction, negative 2 in the complex direction. This length is going to be called r like it was before when we were converting from rectangular to polar form. This angle alpha is going to be used because it's in the triangle, but we're going to actually measure theta from the positive x-axis all the way around. So let's find r, which is the absolute value of this complex number. So x squared plus y squared is r squared, x is 2, y is negative 2, but its length is 2, so you could call it x squared plus y squared is r squared, 2 squared plus 2 squared is r squared. 4 plus 4 is r squared, 8 is r squared, so the square root of 8 is r. That is the absolute value of this complex number. To simplify that, root 8 is root 4 times root 2, or 2 root 2. So again, the absolute value of the complex number is 2 root 2. Now we've got to find the angle measured from the positive x-axis. But we're going to use alpha here as a shortcut. So the tangent is opposite over adjacent. Tangent of alpha, this length is 2, that length is 2. Tangent of alpha is 2 over 2. Tangent of alpha is 1, alpha is pi over 4, but actually we prefer degrees when working with complex numbers. So I'll call alpha 45 degrees. Now what is theta measured from here all the way around? That would be 360 minus 45 degrees. So we have r in that form, we have theta in that form. And we can express complex numbers in the r cis theta form. So z1 can be thought of as 2 root 2 cis 315 degrees. Cis is shortcut notation for cos theta plus I times the sine of theta. So that's cos 315 degrees plus I times the sine of 315 degrees. And that's our polar form for that complex number, 2 minus 2i. Also can be expressed as 2 root 2 times cos 315 degrees plus I times the sine of 315 degrees. Next up we have negative 2 plus 2 root 3i. Negative 2 in the real direction, 2 root 3 in the imaginary direction. And we want to find the absolute value of that complex number. We want to find r. So x squared plus y squared is r squared. So we have, I used negatives here, fine. Negative 2 squared plus 2 root 3 squared is r squared. 2 squared is 4, root 3 squared is 3, 4 times 3 is 12, 4 plus 12 is r squared, 16 is r squared, r is 4. I'm going to find alpha, but remember I really want theta measured from the positive x-axis, which should be back that way. But looking at this, the tangent of alpha is 2 root 3 over 2, the length there is 2. So tangent of alpha is root 3, which would mean alpha is 60 degrees. Theta, measured from the positive x-axis, would be 180 minus 60 degrees, or 120. So we get z2 is 4 cis 120 degrees, 4 times cos 120 degrees plus I times the sine of 120 degrees is the formal version for that. And next we have z3 is negative 5i. So here's the real number line, but there's nothing, it's 0, and then it drops 5 in the imaginary direction. The length of this, I hope, is obviously 5, but if you want to see it come, there's the long form, 0 in the real direction, -5 in the imaginary direction, 0 minus 5i. You could say x squared plus y squared is r squared. 0 squared plus -5 squared is r squared. And we get 5 as r. The angle, I'm not even going to go ahead and use tangent. Just take a look at this. Starting at the positive x-axis all the way here, 0, 90, 180, 270 degrees. The angle theta there is 270 degrees. So this complex number could be thought of as r cis theta, 5 cis 270 degrees. Writing it longhand, of course, 5 cos 270 plus I times the sine of 270. And you'll notice the cos of 270 is 0. Sine of 270 is -1, so you'd get 5 times -1 times I, -5i. It matches. Now, here are two of the complex numbers we have. We have z1 and z2 with the cis form. And I want to take a look at z1 times z2, and my goal is to express that in polar form. If you multiply two complex numbers, multiply their absolute values, multiply the r's, 2 root 2 times 4, and then add the angles. So 2 root 2 times 4 is 8 root 2. Cis 315 plus 120 is 435 degrees. So I get z1 times z2 is 8 root 2 cis 435. But let's throw out 360 because 435 degrees is coterminal with something between 0 and 360. So if I throw that out, I am left with 75. So in polar form, z1 times z2 is 8 root 2 cis 75 degrees. Formally, 8 root 2 times cos 75 degrees plus I times the sine of 75 degrees. Next up, I have z1 and z3, and I want to divide them. If you're dividing complex numbers, you divide the absolute values, you divide the r's, 2 root 2 over 5, and then subtract the angles. So 315 minus 270 just gives us what? Just gives us 45 degrees. So we certainly could simplify that because we know what the cosine of 45 degrees and the sine of 45 degrees. But all we wanted here was the polar form. So let's rewrite that as cos 45 plus I times the sine of 45. So z1 divided by z3 modulus 2 root 2 over 5 times cis 45, which means cos 45 plus I times the sine of 45 degrees. Here we have z1 is 2 root 2 cis 315 degrees. And I want to take z1 to the 4th power, which is going to require us to take the absolute value to the 4th power, and then 4 versions of 315 degrees. So we'll get 2 root 2 to the 4th power, cis 315 times 4. Now, what is this? 2 to the 4th is 16. Root 2 to the 4th is going to take some work, but that's root 2, which is 2. Root 2 is another 2. So root 2 to the 4th is just 4. 2 to the 4th is 16. Cis 4 times 315 degrees. What's that going to give us? Cis 1260. So you're going to throw out 360 and throw out another 360. Probably another 360. And what's that going to leave us? 16 times 4. Cis 180. Now, once that's the case, 16 times 4 is 64, cis 180. But cis 180 is one we certainly can do. Cosine 180 plus I times the sine of 180. Cosine of 180 is -1. Sine of 180 is 0. So we have 64 times -1 plus I times 0, which is just going to give me -64, which is kind of interesting. This complex number to the 4th power just turns out to be -64. If we want to write it in a plus bi form, that's -64 plus 0i. And we have z2 here is 4 cis 120. We want to do z2 to the 5th power. So let's think about this for a minute. That'll be 4 to the 5th power, cis 120 times 5. That's 600 degrees. Throw out 360, and then where does that leave us? 4 to the 5th is a large number. 4 to the 5th is 1024. So we have 1024 cis 600 degrees. Well, throwing out 360, that leaves us what, with 240? So we have z2 to the fifth is 1024 cis 240, which is, of course, cos 240 plus I times the sine of 240. So we want to simplify this. We want to write it in a plus bi form. So we're going to need to find out what is the cos of 240 and what is the sine of 240. 240 degrees is in the third quadrant, so that should help us get us to where we need to be. Reference angle, well, 180 to 240 is 60, so the reference angle here is 60 degrees. So in quadrant 3, cosine is negative. So cos of 240 is the negative of the cos of the reference angle. Negative cos of 60. Cos of 60 is 1/2. So the cos of 240 is equal to negative 1/2. How about the sine of 240? In quadrant 3, sine is also negative. So negative sine of the reference angle of 60, and the sine of 60 is root 3 over 2. So the sine of 240 is negative root 3 over 2. So we will replace cos 240 with negative 1/2. We'll replace sine 240 with negative root 3 over 2. Then distributing this, we get z2 to the fifth power is 1024 times negative 1/2. That's what, negative 512. Plus 1024 times I times negative root 3 over 2. That's negative 512 root 3I. And that completes the lesson, and that completes the review.